Now moving on to section 5.5, which is going to deal with a certain kind of series called the alternating series. And what this is pretty much is my signs are going to switch. We saw a few of these in section 5.2. Basically, like I said, our signs are just going to switch. Positive to negative to positive to negative, on and on. There's a typo on that one right here. If it's just an in, it's going to start negative, positive, negative, positive. So just keep that in mind. There's a typo there. My fault. Negative, positive, negative, positive, negative, on and on. So basically, I want to learn now, how do I tell if something like this converges or diverges? For that, I'm going to use something called the alternating series test. And what this says, an alternating series converges if Bn plus 1 is less than Bn. What this means is I'm decreasing, right? Because my next term is going to be smaller, and then smaller, smaller, smaller. So this means it's decreasing. Number two, the limit as n goes to infinity of Bn. And again, Bn is everything without the minus sign, is what it is. If the limit of that is equal to 0. So both of these have to be true. Both of them. So example 1, for each of the following alternating series, determine whether the series converges or diverges. So example 1a, sum of negative 1 to the n plus 1 over n squared. So again, I'm looking at the Bn, and Bn is everything without the minus 1. So on top, I would just have 1 over the n squared. So I'm looking at that. First thing I want to test is that it is decreasing. That's my first thing. So if I plug in a 1, 1 over 1 squared is 1. Plug in a 2, 1 over 2 squared is 1/4. Plug in a 3, 1 over 3 squared is 1/9. Then I'd have 1/16, 1/25, on and on. This is clearly getting smaller. So that's good. My first rule is good. I'm decreasing, which is good. The next one, I'm going to take the limit as n goes to infinity. Well, as this gets really big, the whole thing is really small. So 0, which is what I wanted. So that's also good. Therefore, this converges by the alternating series test. It's that quick, that simple there. Example B, it's the sum from n equals 1 to infinity of negative 1 to the n plus 1, n over n plus 1. So for this one, again, our Bn is just everything except for that, so n over n plus 1. Let's list some terms there. Plug in a 1, you get 1/2. Plug in a 2, you get 2/3. Plug in a 3, you get 3/4, and then 4/5, on and on. Notice here, this is increasing. So I can go ahead and already stop and say this diverges by the alternating series test. Because my terms are growing, so no good. Example 1c. Sum from n equals 1 to infinity of negative 1 to the n plus 1 times n over 2 to the n. So again, my Bn is going to be n over 2 to the n. Let's start to list out a few terms. Plug in a 1, you get 1 over 2. Plug in a 2, you get 2 over 2 squared, which is 2 over 4, which is 1 over 2. Plug in a 3, you get 3 over 2 to the third, so 3 over 8. Plug in a 4, 4 over 2 to the fourth, which is 4 over 16, which is 1 over 4. Plug in a 5, you get 5 over 32, on and on. And as I can see, that is decreasing. So that's good. And then let's take the limit. 2 to the n grows at a faster rate than n does, so the bottom is going to be really large, which means the whole thing is really small. So that's it. It converges. So with these, though, sometimes I want to know a little bit more. That isn't hard enough. Let's make it a little harder, okay? So sometimes I want to know a little bit more. So let's define a new word. A series exhibits absolute convergence if the series of the absolute value converges. A series conditionally converges if an converges but the absolute value diverges. And then if neither one of them do, of course, it still diverges. And there's a fact, if the absolute value converges, then the regular an also does. So if I want to test for absolute convergence, I've got to do the absolute value to start with. I'm going to start with that. So example number 2, for each of the following series, determine whether the series converges absolutely, converges conditionally, or diverges. All right, so let's do some example of that. Example number 2, for each of the following, determine whether the series converges absolutely, converges conditionally, or diverges. So let's do 2a first. Sum from n equals 1 to infinity of negative 1 to the n plus 1 over 3n plus 1. Okay, so first things first, I want to test for absolute convergence. Absolute. So this is looking at the sum of the absolute value. Well, think about what the absolute value is going to do, right? What it's going to do is basically all my terms are going to be positive. So it's as if this first one isn't even there. So this is looking at the sum, n equals 1 to infinity, of 1 over 3n plus 1. So let's look at that. Okay. So there are several ways I could do this. I could use the integral test. I could use the comparison test. There's a lot I can do. Let's do the comparison test. So let's compare 1 over 3n plus 1. I have n to the first, so let's compare it to 1 over n. Okay. Well, eventually I can see right here 3n plus 1 is definitely larger than n, right? Therefore, 1 over 3n plus 1 is definitely going to be smaller. So I have found a series that's larger, and I know this diverges. But remember that doesn't really help me. If it's going to be larger, I want it to converge. So if that didn't help me, let's try something else. Let's do the limit comparison test and still use bn equals 1 over n. So then what that means is I'm doing the limit as n goes to infinity of an, which is 1 over 3n plus 1, times, flip that, and you get n over 1. That's going to be the limit as n goes to infinity. My largest term on top is an n. My largest term down here is 3n. N's cancel out, and I get 1/3. So since I got a number, what this means is that whatever bn does, an does too. Well, I know bn is harmonic, which means it diverges. Therefore, this is also going to diverge. So what this means is I know this is not absolutely convergent. So now let's test for conditional. Conditional is looking at just the regular series by itself. Well, this series is alternating. So use the alternating series test. Bn there is 1 over 3n plus 1. I've got to check and make sure it is decreasing to start with. Plug in a 1, you get 1 over 4. Plug in a 2, you get 1 over 7. Plug in a 3, you get 1 over 10, and then 1 over 13, on and on. That is decreasing, so that's good. And then make sure the limit is equal to 0, which it is, because as the bottom gets really big, the whole thing is really small. So that's also good. So that means it is conditionally convergent, because my first part didn't work, but the second part did. Try example B. Example B is going to be the sum from n equals 1 to infinity of cosine of n over n squared. So for absolute, remember we're going to do the absolute value. The good thing about n squared is always going to be positive, right? But cosine goes up and down. So cosine, I'm going to have to leave the absolute value there because it might be a negative. So absolute value, cosine n over, but this is always positive, so I can just leave it as n squared. So now I can use the comparison test there. Let's let bn be equal to 1 over n squared. So let's look at absolute value cosine of n over n squared compared to 1 over n squared. Well, I know cosine is always between -1 and a 1, right? So this is always less than 1. So it goes like this. This is a p series with p equals 2, so it converges. I have found a larger one that converges, so this one also converges. Since it worked on the first try, this has absolute convergence. One more example, and then that's it for this section. Sum from n equals 1 to infinity of -1 to the n plus 1, n over 2n cubed plus 1. So let's start with absolute, see if that works. That's the sum, n equals 1 to infinity, absolute value. So all that's going to do is get rid of the negative. So n over 2n cubed plus 1. So now I've got to see what happens with that one. Let's do the limit comparison test. I have n over n to the third. So let's use bn as 1 over n squared. Again, because I have an n here, n to the third there. So if you canceled them out, you'd be left with 1 over n squared. So that's why. So let's do the limit as n goes to infinity of an, which is n over 2n cubed plus 1, times flip the bn. That's going to be the limit as n goes to infinity. N times n squared is n cubed. And then this is just 2n cubed plus 1. The largest term on top is n to the third. Largest term on the bottom is 2n to the third. They cancel out to give us 1/2. So since I got a value there, bn is going to do the same as an. bn converges because it is a p series with p equal 2. So this is also going to converge. So this converges absolutely. If any of that does not make sense, let me know.